stop for a second. Just stop moving. Feel your feet on the floor right now. That solid, constant pressure pushing back against you. It's so normal, so completely ordinary, that you probably haven't actually felt it in years. It's just there, always. The background noise of existence. Now lift your arm. Feel that? That subtle weight pulling it down? That quiet resistance in your shoulder fighting against something that has never stopped pulling on you, not for a single heartbeat, since the moment you were born? That's your oldest relationship, your first companion. The invisible force that's been holding you since before you even knew what holding meant. This is gravity. Simple, right? Predictable. Obvious. Just down. But here's where it gets weird. What if that's not what gravity is? What if that pull you're feeling right now, that constant downward tug, is just what gravity feels like? Here? What if gravity isn't a force at all? What if everything you think you know about why things fall, why planets orbit, why you're stuck to this spinning rock hurtling through space, is wrong? Not slightly wrong. Fundamentally, beautifully, mind-bendingly wrong. Because here's the truth. Gravity doesn't pull. It never has. If your brain just did a backflip, do me a favour, hit that like button and subscribe. This is about to get way stranger, and you're not going to want to miss it. Also, real quick, where are you watching this from? What part of Earth is gravity holding you to right now? Drop a comment. I genuinely read every single one. All right. Let's figure out what gravity actually is. We are starting from a place of absolute trust. Gravity is the silent stage manager of our daily lives. It is present in the way your feet meet the ground in the morning, in the arc of a dropped pen, in the quiet certainty that a book will remain on a table until you move it. There is no fanfare to its presence, no hum, no vibration, no visible signal threading its way from the centre of the earth to the soles of your shoes. Instead, gravity feels like the default condition of existence itself, so utterly reliable that it fades into the background of awareness, like the pressure of the air or the passage of time. You notice it mostly in its absence, or when something goes wrong, the slip of a glass from a hand, the stumble on a stair. These events feel inevitable, as if they could not happen any other way. And so, over years, over a lifetime, the mind stops questioning them. Gravity becomes not just familiar, but expected. It appears uniform. Absolute. This sense of constancy is reinforced by every mundane experience. A cup of coffee weighs the same in your kitchen as it does in your garden. Your body feels no lighter when you sit, no heavier when you stand. From our human perspective, gravity seems fixed, a rule written into the fabric of reality that simply is. Yet, this is the first gentle illusion we must unravel. Even here, on this one world, gravity is not perfectly uniform. Its strength wavers, subtly, depending on where you are. At the equator, the planet's spin and its slightly bulging shape mean the pull is marginally weaker than at the poles. On a mountain top, because you are fractionally farther from Earth's heart, the grip relaxes, just a little. These differences are real, measurable with exquisite instruments, but they are far, far below the threshold your body can sense. The reason gravity feels so constant is not because it is truly unchanging, but because our perception is exquisitely limited, tuned to a narrow band of experience. The variations that exist are smoothed out by the scale of our lives. Our muscles, our bones, our very sense of balance, they all adapted to this specific gravitational environment and treat it as the one and only normal. Over a lifetime, that normal becomes invisible. Historically, our understanding began not with this invisible background, but by seeing it as an actor. In the late 17th century, Isaac Newton described gravity as a universal attraction. Every piece of matter, he proposed, pulls on every other piece. The strength of that pull grows with mass and fades with distance. It was a revolutionary leap. It united the fall of an apple with the orbit of the moon. The same force that gathered objects to the ground also governed the celestial dance overhead. Gravity was no longer just a local phenomenon. It was universal, a cosmic rule. For centuries this idea worked. It predicted the paths of comets, the motion of planets, the tides. It explained why, near Earth's surface, everything accelerates downward at roughly the same rate. For practical purposes, it was, and in many ways still is, brilliantly accurate. But this powerful idea also reinforced a subtle intuition that gravity behaves the same everywhere. The equations allowed for variation, yes, but the underlying picture was of a single, consistent force, a uniform rule applied across the blank canvas of space. It made our everyday feeling that gravity is a fixed property seem like a cosmic truth. In reality, the gravity we experience on Earth represents only one local expression of something far deeper. Earth is a medium-sized rocky planet with a specific mass, a specific radius, a particular inner architecture. Its gravity is strong enough to hold a thick atmosphere, to shape vast oceans, to anchor life to its surface, but not so strong as to crush our structures or make movement impossible. This balance feels natural, inevitable, only because life evolved within it, was sculpted by it. Imagine, for a moment, a different Earth. If our planet were slightly more massive, gravity would tighten its grip. Everything would weigh more. A simple walk would be a laborious trek. The architecture of trees, the skeletons of animals, the very flow of rivers, all would be shaped by a heavier hand. If Earth were less massive, the opposite would unfold. Objects would fall in slow, dreamy arcs. A jump could carry you dauntingly high. The atmosphere might be thin, or perhaps unable to hold on at all, bleeding away into the void. Small changes in planetary mass lead to profound changes in the gravitational experience. Because our world provides such a stable, such a narrow range of conditions, it is the easiest thing in the world to mistake that local balance for a universal standard. It feels constant because it has been constant for every single one of our ancestors, for every living thing we have ever known. But that constancy is local, a gift of our particular place, and the limits of our lived experience are vanishingly small when compared to the range of environments the universe contains. Even within our own solar system, just next door in cosmic terms, gravity sheds its uniform mask. Consider the moon. Its gravity is a mere fraction of Earth's. There, an astronaut can lift themselves with their own legs, can bound across the dust in great floating leaps. A dropped tool takes its time, drifting down in a graceful, slow-motion arc. Now turn to Jupiter. A giant. A behemoth. Its gravity is not just stronger, it is a dominant crushing force. At the level of its cloud tops, where there is no solid ground to stand on, the pull is more than twice that of Earth. A person there would feel profoundly, unbearably heavy. These are not different laws of physics. They are the same law, responding to different numbers. More mass, stronger pull. Different size, different surface gravity. The key is this. Gravity is not something that simply exists at one strength. It is a relationship. It depends utterly on the properties of the objects involved. Mass, distance, distribution, they all matter. The gravity you feel right now is the result of Earth's particular combination of these factors. It is not the default setting of the universe. It is our local custom. Understanding this, that gravity is a local experience rather than a universal constant, opens a door. It invites a quiet curiosity. If gravity can feel so different on the Moon and on Jupiter, what other expressions does it have? What does it feel like at the heart of a star? In the emptiness between galaxies, at the edge of a place where gravity becomes so intense that not even light can leave. The familiar downward pull begins to transform. It becomes one example among many, a single note in a vast cosmic chord. By starting from what feels most obvious, most dependable, we can gently, patiently question those very assumptions. Gravity does not change abruptly from place to place. It transitions smoothly, meaningfully. The version experienced here is not wrong. It is not incomplete. But it is specific. It belongs to this planet, at this distance from its centre, with this mass beneath our feet. Recognizing that fact does not make gravity less reliable. Instead, it places our experience in context. Gravity remains one of the most consistent features of the universe, but consistency does not mean uniformity. What feels constant here is part of a much wider, richer pattern, a pattern that stretches far beyond the ground beneath you, woven into the fabric of space and time itself. To see that pattern, we must look deeper than the force that pulls apples from trees. We must look at what gravity actually is. Often, we speak of gravity as a force, an invisible tether pulling objects together across empty space. This description works. It gets the job done. But it is not the deepest story. In modern physics, gravity is not treated as a mechanical pull acting at a distance. Instead, it is understood as something more fundamental, something that emerges from the very structure of the universe. To see why this distinction matters, think of other forces. When you push a door, your hand makes contact. When a magnet tugs on a fridge, there is a field you can map, an interaction that weakens quickly as you step away. Gravity is different. It acts between objects, regardless of what lies between them. It cannot be blocked, shielded, or turned off. Its influence extends across vast, perfect vacuums, shaping the motion of planets, stars, whole galaxies. Newton's framework described how gravity behaves with stunning accuracy, but it left a haunting question unanswered. What is it? It treated gravity as a force acting instantaneously across space, without a mechanism, a ghostly influence with no medium. In the early 20th century, Albert Einstein offered a radically different picture. He proposed that gravity is not a force playing out on the stage of space and time, but a consequence of the shape of the stage itself. This is the heart of general relativity. In this view, space and time are not separate, passive backgrounds. They are fused into a single dynamic entity, space-time. And space-time is not rigid. It can be stretched, compressed, curved. Mass and energy tell space-time how to curve, and that curvature tells matter how to move. Here is the profound shift. Objects do not fall because they are pulled by a force. They fall because they are following the straightest possible paths through a space-time that is curved by Earth's mass. These paths are called geodesics. To us, embedded within that curved space-time, this motion looks and feels exactly like acceleration, like a force pulling us down. But from the universe's perspective, a falling object is simply moving freely, following the natural contours of the geometry around it. This idea can feel abstract. We cannot see or touch curved space-time. But its effects are measurable, precise, and inescapable. One of the most stunning insights of this view is that gravity affects not just motion, but time itself. Clocks tick at different rates depending on how deep they are in a gravitational field. Time runs slightly slower closer to a massive object, slightly faster farther away. This gravitational time dilation is not a theory, It is a measured fact. Your phone's GPS would fail within minutes if the satellites overhead did not constantly correct for the fact that their clocks, being higher in Earth's gravity, tick faster than clocks on the ground. The difference is tiny, but it is there, woven into the ticking of every second. The difference between Newton's gravity and Einstein's is not that one is wrong and the other right. Newton's description is a magnificent approximation, incredibly accurate when gravity is weak and speeds are low, which is almost everywhere in our daily lives. Einstein's description becomes essential when gravity is intense, distances are vast, or precision is extreme. On Earth, the difference is hidden. The curvature of space-time is so gentle that objects still seem to just fall down. Orbits appear as simple circles and ellipses. The force-based picture continues to work perfectly. This is precisely why gravity feels so simple and intuitive at human scales. The deeper geometric reality is hidden beneath effects too small for our senses to notice. Space-time itself is not a passive stage. It is a dynamic, responsive entity. Earth's mass creates a dimple in it, a gentle warp. The moon moves through that warped geometry. It is not being pulled by a rope, it is rolling along a curved contour, like a marble in a bowl. The moon's path is the straightest line it can take through a space-time that has been shaped by our planet. This provides a beautiful, natural explanation for why gravity varies. Where space-time is more curved, gravity appears stronger. Where it is flatter, gravity appears weaker. There is no gravitational substance flowing between objects. No particles carrying the force in the usual sense. Instead, there is this continuous, invisible geometry that governs motion everywhere. Objects respond to that structure simply by being within it. One way to grasp this is to imagine motion without any gravity at all. In flat, empty space-time, an object moves in a straight line at constant speed forever. That is the natural state of motion. What gravity does is change what counts as a straight line by warping the very arena through which everything moves. What looks curved or accelerated to us is, in the full geometry, the straightest possible path. This perspective also clarifies why gravity cannot be switched off. As long as mass and energy exist, space-time will have structure. As long as space-time has structure, motion will be guided by that structure. Gravity is not a feature added to the universe. It is woven into its most fundamental fabric. And this geometric view predicts things Newton's never could. The bending of starlight around the sun, the precise way Mercury's orbit wobbles, the existence of black holes. These predictions have been confirmed again and again, tying the theory to the real world with unbreakable knots. So, we find ourselves with two powerful ways of seeing. One, a force that pulls, intuitive and immensely practical. The other, a geometry that guides, profound and deeply true. They are not in conflict. They are layers of understanding. The geometric view explains why the force-based view works so well here, and why it ultimately gives way to stranger truths elsewhere. It allows gravity to feel steady and uniform on Earth, while accommodating the dramatic, almost unimaginable variations that exist across the cosmos. By moving from a force to a geometry, gravity becomes something both simpler, no spooky action at a distance, and more profound, tying together space, time, motion and mass into a single elegant framework. The sensation in your feet, the weight in your hands, the fall of leaves in autumn, they all remain exactly as they are, exactly as you've always known them. What changes is the explanation beneath them. In this light, gravity is not something acting within the universe. It is part of what the universe is. And because the universe is not uniform, because objects differ wildly in mass, because they are scattered across impossible distances, gravity cannot be uniform either. What feels steady and unchanging here is the result of very specific, and not particularly common, conditions. Your sense of constancy is a gift of your address in the cosmos. Let's make this relationship tangible. In its simplest, most universal terms, gravity depends on two things: how much mass is involved and how far apart things are. More mass means a stronger influence. Greater distance weakens that influence rapidly. This is clear in Newton's equation, and it remains valid even in Einstein's geometric universe. On Earth, the distance from the planet's centre changes so little during your day, standing, sitting, climbing stairs, that the variation is insignificant. Earth's mass is huge, and your movement across its surface is trivial in comparison. So, gravity feels constant. The changes are there, but they are whispers in a roar. But as distance grows, gravity's whisper fades. It does not vanish, not ever. It weakens gradually, following a predictable, smooth decline. There is no boundary, no line where gravity stops. It just becomes quieter, and quieter, and quieter. The moon is a perfect example. It is hundreds of thousands of kilometres away, yet Earth's gravity, weakened by that distance but still potent, holds it in orbit. The moon, in turn, exerts its own pull on our world, tugging on the oceans to create the tides. This is a mutual dance, an influence stretching across a profound emptiness. Move farther out, to the distance of the sun, and Earth's own gravity becomes a negligible murmur in a much louder conversation. The sun's mass is so immense that it dominates, its gravitational voice shaping the paths of every planet, asteroid, and comet for light years around. This pattern repeats, scales up, echoes through the cosmos. A small asteroid exerts a barely there tug. A planet exerts more. A star commands a region of space. A galaxy, with its hundreds of billions of stars, bends space-time across hundreds of thousands of light-years. At each step, the same two factors, mass and distance, orchestrate the behaviour. The weakening is smooth, endless. There is no sudden cut-off, which is why gravity is so hard to picture. Our intuition is built on contact forces. A push stops when hands part. A magnetic grip fades within a room. Gravity does not obey such limits. Its influence extends outward forever, thinning like a scent on the wind, but never, ever reaching zero. To describe this pervasive influence, we use the idea of a gravitational field. Think of it not as a substance, but as a map, a description of the strength and direction of gravity's pull at every point in space around a mass. Near a planet, the field is strong and pointed inward. Far away, it is weak and diffuse. Where many masses exist, their fields overlap and combine into complex landscapes. The gravity you feel right now is the net result of all these fields at your location. On Earth's surface, our planet's field is so overwhelmingly dominant that the tiny contributions from the moon, the sun, and distant planets are imperceptible without tools. This dominance creates the beautiful illusion of simplicity. But change the environment, and the balance shifts. On the moon, Earth's field is still a major player, competing with the moon's own weaker field. In deep space, far from any large body, fields become faint, and motion is a gentle drift governed by the faintest of tugs from the nearest, most massive object. From the geometric view, this variation is simply a change in the curvature of space-time. Mass makes a dent. A bigger mass makes a deeper, wider dent. Close to that mass, the curvature is steep, and paths bend sharply. Far away, the dent shallows out, and space-time flattens toward its natural state. The transition is smooth, continuous, and utterly predictable. This is why gravity cannot be uniform. The universe is filled with dents of every conceivable depth and size, overlapping and interfering in an infinitely complex landscape. There is no single gravitational environment. Every location, every point in space, has its own unique gravitational signature, shaped by what is nearby and what is far away, by what is seen and what is hidden. This leads to a quiet, powerful realization. Gravity is always, fundamentally, local. It is shaped by your immediate surroundings, by the distribution of mass in your cosmic neighbourhood. The gravity you experience is not a universal constant imposed from outside. It is the sum of the universe acting on you, right here, right now, through the geometry of mass and distance. This locality is the secret. It explains why gravity can feel so utterly dependable, while also being so fantastically variable. In any one place, if the masses are large and stable and the distances don't change much, the gravitational environment is stable. It appears fixed. But travel to another place, with a different arrangement of mass, and the experience changes. The laws haven't changed. The universe, understanding gravity as something that varies with context, builds a bridge. It connects the solid ground beneath you to the alien soil of Mars, to the cloud tops of Jupiter, to the void between stars. It shows that the steady pull you've known all your life is not an exception, nor is it the rule. It is one outcome, one possibility. The same principles apply everywhere, but their effects depend entirely on where you are standing and what is around you. Gravity does not behave differently because the laws flip. It behaves differently because the universe is not the same from one place to the next. We have built our intuition inside a very special, very narrow room. It is time to open the door and step outside to see how gravity expresses itself when the conditions of our room no longer apply. Our first steps will be close to home, within our own solar system, where the familiar rules paint astonishingly different pictures on different worlds. We begin our journey outward, in the most familiar of unfamiliar places, our own solar system. Here, within the gravitational sway of our sun, we find a natural laboratory, a collection of worlds where the same physical principles we know on Earth play out with different numbers, yielding experiences that range from the buoyantly strange to the crushingly intense. By visiting these neighbouring worlds in our minds, we can feel the variability of gravity in an immediate, tangible way. It stops being an abstract equation and becomes a spectrum of physical sensation, shaped not just by size, but by the deeper secrets of density, composition, and inner history. Earth, of course, is our baseline. Its particular blend of mass and radius produces a surface gravity of 9.8 meters per second squared. This is the force our muscles are tuned to fight, the pull our bones evolved to withstand, the rhythm to which our blood circulates. It feels neither trivial nor overwhelming. It simply is. A dropped object falls at a pace that seems natural. A jump has a satisfying bounded arc. This balance is so ingrained that we mistake it for the default setting of reality. But it is merely our local custom, a product of this specific world. Change the ingredients of the world, and the custom changes dramatically. Our first and clearest contrast hangs in the night sky, the moon. With only about 1/80th of Earth's mass and a smaller radius, its surface gravity is a gentle 1/6 of our own. Imagine holding an object that weighs 6 kilograms on Earth. On the moon it would feel like 1 kilogram. You could hold it aloft with a finger. This is not a small difference, it is transformative. The Apollo astronauts experienced it the moment they stepped onto the lunar dust. Their movements, trained for Earth, became comically exaggerated. A simple step turned into a slow, bounding hop. A stumble became a graceful, low-gravity ballet. Dropping a hammer, they watched it drift to the ground as if sinking through water. This reduced gravity isn't just about the moon being smaller, it speaks to its inner story. The moon is less dense than Earth, with a smaller, cooler metallic core and a simpler, quieter geological past. Less mass is packed into that smaller volume, so the gravitational grip at the surface is gentle. It is a world where gravity is present, undeniable. It holds the atmosphere less landscaped together and keeps the astronauts from floating away, but it is weak enough to rewrite the rules of motion. It is a whisper where Earth's is a murmur. Next, we set our sights on the red planet, Mars. Larger than the Moon, but only half the diameter of Earth, Mars offers a middle ground. Its surface gravity is about 38% of Earth's. A person weighing 100 kilograms here would feel like a manageable 38 kilograms there. This is a profound change, yet not so extreme as to be wholly alien. Walking on Mars would feel light, energetic. Each step would carry you farther. Each jump would have a higher, lingering apex. Over time, your body would adapt, your muscles learning a new normal, your bones experiencing a reduced load. Mars teaches us that composition matters as much as size. Despite being larger than the Moon, Mars has a lower overall density. Its core is smaller relative to its size. So, while it looks more substantial, its gravitational pull is more modest than its diameter might suggest. Robotic emissaries, the Viking landers, the Spirit and Opportunity rovers, the car-sized Curiosity and Perseverance, have not just photographed this world, they have measured its gravitational field with precision, confirming that it aligns perfectly with the mass we infer from its orbit and composition. Their data paints a picture of a world where gravity is different, but not unrecognisable. A world where you would feel lighter, freer, but still fundamentally grounded. Now, we turn to the giants, and here intuition begins to strain. Jupiter, the king of our solar system, has no solid surface in any conventional sense. But if you could somehow stand at the level of its cloud tops, you would feel a gravity more than 2.5 times stronger than Earth's. That person who weighs 100 kilograms on Earth would feel like 250 kilograms there. Every movement would be a slog, a labour against a relentless heavy hand. This immense pull comes from Jupiter's staggering mass. It is over 300 times the mass of Earth. Although it is made mostly of lightweight hydrogen and helium, and its average density is actually lower than Earth's, the sheer incomprehensible volume of material creates a gravitational well of immense depth and power. Jupiter's gravity doesn't just shape its own banded atmosphere and raging storms, it dominates the solar system after the Sun itself. It shepherds asteroids, captures comets, and its pull shapes the orbits of its many moons with tyrannical force. It is a gravitational sovereign. Saturn, jewel of the heavens, presents a fascinating counterpoint. It is nearly as large as Jupiter, but its surface gravity at the cloud tops is only slightly greater than Earth's. How can this be? The answer is density. Saturn is the least dense planet in our system. It is so light that if you could find an ocean large enough, it would float. Its mass is significantly less than Jupiter's. This comparison is crucial. Size alone does not dictate surface gravity. A larger planet can have a weaker pull if its material is spread more thinly, less compactly. It is the combination of mass and radius, the concentration of matter, that writes the final number. From these neighbouring worlds, a clear, elegant pattern emerges. Surface gravity is a dialogue between two factors, the total mass of the object and the distance you are from its centre. That distance is, for a world with a surface, its radius. The relationship is captured in a simple ratio, mass divided by radius squared. Two planets of similar size can feel radically different if one is made of dense rock and metal, and the other of light gas and ice. Two planets with similar surface gravity can look utterly alien to one another, one a small, dense ball of iron, the other a vast, fluffy globe of hydrogen. Gravity is sensitive to what lies beneath, to the hidden architecture of a world. It is a diagnostic tool, a way of weighing a planet from afar, of listening to the story of its formation whispered through its pull. These planetary examples make the abstract physical. Gravity is no longer just a chapter in a physics textbook or a curvature in a mathematician's model. It is something you could feel in your legs on Mars, in your lungs on Jupiter. The solar system, in its beautiful variety, demonstrates gravity's variability without our having to leave home. Each world is a different answer to the same equation, a different outcome sculpted by history, collision, and cooling. Together, they show that even within the reach of a single star, gravity has many dialects. But to see gravity truly at work, to see it not as a surface condition, but as an internal, creative and destructive force, we must look not at the cold, solid surfaces of planets, but into the heart of the furnace that lights them all, a star. From a distance, a star like our Sun appears serene, constant, a steady point of light. But beneath that placid surface, gravity is engaged in a titanic, balancing act of unimaginable scale and ferocity. Inside a star, gravity is not a one-way pull toward a surface, it is a pervasive inward pressure that fills every cubic centimetre. A star begins its life because of gravity. A vast, cold cloud of gas and dust, light years across, begins to contract under its own weak self-attraction. As it shrinks, the gravitational pull in its core strengthens, drawing more material in, raising the density and temperature. This is a runaway process, a gravitational collapse. For a body like our Sun, this collapse continues until the core becomes so hot and dense that atomic nuclei, which normally repel each other fiercely, are forced together. Nuclear fusion ignites. Hydrogen atoms fuse into helium, releasing a torrent of energy. At this moment, gravity does not retire. It finds a partner. The energy released by fusion creates an immense outward pressure, a radiation and thermal force that pushes back against the relentless inward crush of gravity. The star finds a balance, a state known as hydrostatic equilibrium. It is this exquisite dynamic balance that allows a star to shine steadily for millions or billions of years. It is not a static truce. It is a constant, moment-by-moment negotiation. If the core contracts a tiny bit, the temperature rises, fusion rates increase, and the outward pressure builds, pushing the core back out. If the core expands, it cools, fusion slows, and gravity gains the upper hand, compressing it once more. The star is a self-regulating furnace, and gravity is the unyielding foreman, ensuring the fire burns at just the right rate. The strength of gravity inside a star is dictated by its total mass. A more massive star has a stronger gravitational pull throughout its interior. This increased gravitational pressure squeezes the core harder, making it hotter and dramatically accelerating the rate of nuclear fusion. A massive star lives fast and dies young, shining with blinding brilliance for only a few million years before exhausting its fuel. A star like our Sun, with its modest mass, has a gentler internal gravity, one strong enough to sustain fusion, but not so strong as to drive it furiously. Its core temperature of about 15 million degrees Celsius is just right for a steady billion-year fusion of hydrogen. This longevity, this stability, is a gift of its specific gravitational intensity, a window of opportunity long enough for planets to form and, on at least one, for life to arise. Gravity inside stars also choreographs how energy escapes. In some regions, energy travels by radiation, with photons bouncing endlessly between dense particles in a slow, random walk outward. In other regions, the heat is so great that the plasma itself begins to boil, with huge bubbles of hot material rising and cooler material sinking in vast convection currents. The structure of these layers, radiative core, convective zone, is a map drawn by the interplay of gravity, pressure, and temperature. We know this not just from theory, but from listening. Helioseismology, the study of oscillations on the Sun's surface, lets us peer inside. By measuring the ripples and waves that travel through the solar interior, scientists can infer its density, its rotation, its deep currents. It is like taking an ultrasound of the Sun, and the picture confirms that gravity is the fundamental architect, holding the entire seething structure together. This balance, however, is temporary. Gravity is patient, and it is always waiting. As a star ages and its nuclear fuel is gradually transformed, the balance shifts. When the hydrogen in the core is exhausted, fusion slows, the outward pressure weakens. Gravity, unchanging and relentless, seizes the advantage. It compresses the core further, heating it until either new, heavier elements can fuse, helium into carbon, and so on, or if the star is massive enough, until no fusion can withstand the inward crush. In a final, dramatic act, gravity can overwhelm all opposing forces. For a star many times the mass of our Sun, this leads to a catastrophic core collapse and a supernova explosion of staggering violence. Even in this apocalyptic event, gravity is the director, governing the collapse, the rebound, the forging of heavy elements, and the final fate of the core, whether it becomes an incredibly dense neutron star or collapses forever into a black hole. Inside a star, then, gravity's role expands far beyond defining weight. It is the initiator, the regulator, the timekeeper, and the executioner. It sets the conditions for the universe's primary energy source. It determines a star's brightness, its colour, its lifespan, and its ultimate death. The same interaction that gives you weight is the force that lit the Sun, and will one day extinguish it. This reveals gravity's versatility. It operates with the same principles on cold rock and searing plasma. It is a universal language spoken across all forms of matter. But there is another, quieter regime in our solar system, a place where gravity operates at the very edge of its effectiveness. Beyond the planets and their major moons lies a scattered population of small bodies, asteroids, comets, tiny irregular moons. Here, gravity is present, but it is a faint suggestion, a fragile glue. This is the realm of microgravity, where the surface pull can be tens of thousands of times weaker than on Earth. On a small asteroid, a few kilometres across, gravity is barely a force at all. A gentle push could send an object drifting away at a walking pace, never to return. There is not enough mass concentrated in one place to generate a significant pull. The result is a world where weight is almost an abstract concept. Comets, those dirty snowballs of ice, rock and dust, are often just loose rubble piles, held together by a gravitational embrace so weak that when the Sun heats them, jets of gas and dust can erupt with enough force to blow material clear away into space, forming their glorious million-kilometre long tails. Gravity tries to hold the comet together, but thermal forces easily overpower it. In these environments, everything behaves differently. There is no downhill in any meaningful sense. Loose dust does not settle, it can hover above the surface or drift away at the slightest disturbance. A crater, once formed, remains sharp and pristine for eons because there is no strong gravity to trigger erosion or landslides. Walking on such a surface, if you could avoid kicking yourself into orbit, would be a series of slow-motion bounces, a delicate ballet where every step must be calculated to avoid launching yourself into the void. Space missions have given us intimate portraits of this fragile reality. The Japanese Hayabusa probe visited the asteroid Itokawa and found it not to be a solid rock, but a loose rubble pile, a collection of boulders and gravel gently clinging together, its shape looking more like a heap of cosmic debris than a world. The European Space Agency's Rosetta mission orbited Comet 67P/Churyumov-Gerasimenko for years. When it deployed the Philae lander, the comet's gravity was so weak that the lander bounced upon touchdown, its harpoon anchors failing to get a grip in the barely cohesive surface. It was a stark demonstration. On such a body, even the mechanical force of a spring is enough to overcome the gravitational hold. This weak gravity allows for structures impossible on larger worlds. Cavities can persist inside asteroids without collapsing. The entire body can be porous, like a cosmic sponge. Material is barely bound, existing in a delicate state between being a single object and a cloud of drifting fragments. Gravity here is the faintest of tethers, just strong enough to keep things loosely associated over millions of years, but too weak to impose any real order or shape. It is the lower limit of gravitational influence in our everyday cosmos. From the crushing creative heart of a star to the barely there whisper holding an asteroid together, our solar system displays the full, stunning range of gravitational expression. The same fundamental interaction, governed by the same simple rules of mass and distance, produces environments that feel like they belong to different universes. And in every single one, from the inferno to the dust pile, gravity is also shaping motion in a way that, from our earth-bound perspective, seems like a paradox. It is creating not just pull, but perpetual fall. It is creating orbit, and to understand that, we need to revisit our most basic intuition about what falling even means. Orbit feels like a defiance of gravity. We see satellites and space stations gliding smoothly overhead, seemingly suspended in the void, and we call it 0G. It appears as if they have escaped Earth's pull, transcended the force that holds us down. This is one of the most persistent and understandable misconceptions about space. The truth is more beautiful, and it reframes our very idea of what gravity does. An object in orbit is not beyond gravity's reach. It is succumbing to gravity completely. It is in a state of continuous, endless fall. Isaac Newton illustrated this with a thought experiment, Newton's cannon. Imagine a cannon on an impossibly high mountain, above the atmosphere. Fire a cannonball horizontally. It travels forward as gravity pulls it down, and it lands some distance away. Fire it faster. It travels farther before hitting the ground. Now imagine you could fire it with such tremendous speed that, as it falls, the curve of the Earth drops away beneath it at the same rate. The cannonball is always falling toward Earth, but it never gets any closer to the surface, because the surface is curving away. That is orbit. The key insight is the marriage of forward motion and gravitational pull. Gravity isn't being overcome, it is being matched. The orbital path is a balance where the object's inertia, its desire to travel in a straight line, is perfectly countered by the curvature of its path, imposed by gravity. In low Earth orbit, like that of the International Space Station, gravity is still very strong, about 90% of what it is on the ground. The astronauts are not weightless because there's no gravity. They are weightless because they and their spacecraft are all in free fall together. There is no floor pushing up against them to create the sensation of weight. They are falling around the planet, and everything inside the falling capsule is falling at the exact same rate, so it appears to float relative to each other. This condition is more accurately called microgravity or freefall, not zero gravity. The sensation of weightlessness comes from constant, synchronized falling, not from an absence of the force. This view aligns perfectly with Einstein's geometric picture. In curved spacetime, objects follow the straightest possible paths, called geodesics. For the space station, the geodesic around Earth is a closed curve, an orbit. The spacecraft isn't fighting gravity or being held up. It is simply following the natural contour of spacetime shaped by Earth's mass. Gravity isn't a pull, it is a guide. Once placed on the correct path with the right speed, the spacecraft will follow it indefinitely, requiring no engine thrust, simply coasting along the geometry of the universe. This explains why orbits are universal. Moons orbit planets. Planets orbit stars. Stars orbit the centres of galaxies. In each case, the smaller object is falling along a geodesic through the spacetime curved by the larger one. Distance and speed are locked in this gravitational dance. A closer orbit requires a higher speed to avoid falling inward. The Moon, farther away, moves more slowly. These relationships are precise and predictable. The idea feels counterintuitive, because on Earth, falling ends in a sudden stop. In orbit, the scale changes. The planet's curvature becomes part of the equation, and the fall simply never ends. Understanding this dissolves the mystery. Satellites don't hover, they perpetually fall and miss. And when an orbit does decay, from the faint drag of the upper atmosphere for instance, it's not because gravity changes, it's because forward speed is slowly stolen, upsetting the balance. The path then curves more steeply inward until it meets the atmosphere in a final fiery descent. By seeing orbit as guided falling, gravity reveals a subtler nature. It doesn't just restrain, it enables motion. It provides pathways that can keep objects bound together across vast distances without contact, a cosmic glue that works through geometry, not substance. This understanding prepares us to scale up again, to leave our solar system and consider what happens in the true emptiness between stars. Here, our intuition might whisper that gravity must finally fade to nothing, that in the great voids, influence must cease. But gravity knows no such boundaries. Interstellar space, the regions between stars within a galaxy, is vast and mostly empty. Distances are measured in light years, yet gravity is profoundly active here. Stars do not drift aimlessly. They are all in orbit, tracing grand, slow arcs around the shared centre of the Milky Way. Each star feels the combined gravitational pull of billions of other stars, as well as the immense, unseen halo of dark matter that permeates the galaxy. At any point in that emptiness, gravity is the sum of countless overlapping, weakening influences. No single source dominates, but together they create a smooth, pervasive gravitational potential that guides everything. This is why you cannot escape gravity by travelling away from objects. You only change the balance of which objects contribute most to the local field. Scale up once more to the space between galaxies. Intergalactic space is so sparse that a single atom might occupy a volume the size of a wardrobe. Light travels for millions of years without hitting anything. And yet, gravity's hand is still at work. Galaxies move in structured, coherent ways. They gather into clusters, they stream along invisible filaments, they avoid enormous bubble-like voids. These patterns exist because gravity has already acted over billions of years, pulling matter out of the voids and into the dense nodes and threads. The voids are not places without gravity. They are the evidence of gravity's past work. They are empty because gravity emptied them. This idea of overlapping influence is key. Gravity is not a series of isolated spheres of influence. It is a continuous field, a landscape of hills and valleys sculpted by all the mass in the universe, near and far. What we experience at any location is the net slope of that landscape. On Earth, we are deep in a steep, narrow valley carved by our planet. In intergalactic space, we might be on a vast, nearly flat plane, but the gentle tilt of that plane, shaped by galaxies millions of light years away, still guides motion over sufficient time. From the perspective of general relativity, empty space is never truly empty. Space-time exists everywhere. Its geometry is shaped by the total mass-energy content of the universe. In regions with little nearby matter, space-time is very nearly flat, but it is never perfectly universally flat. There is always some residual curvature from distant masses. This is why a spacecraft's path between planets is not a simple straight line. It is a complex curve calculated from the overlapping gravitational fields of the Sun, planets, and even the larger planets like Jupiter. The spacecraft is always moving through a shaped landscape, even when that landscape appears featureless to our eyes. Gravity in these empty spaces plays the long game. Over human timescales, its effects seem negligible. Over millions and billions of years, these weak, persistent tugs accumulate. They pull galaxies into clusters. They draw clusters into superclusters. They weave the largest known structure in the universe, the cosmic web. This brings us to gravity's most majestic role as the architect of the universe's large-scale structure. When we map the universe on the grandest scales, using surveys that plot the positions of millions of galaxies, a stunning pattern emerges. Galaxies are not scattered randomly like sand. They form a vast, interconnected network, long, delicate filaments of galaxies intersecting at dense knots, surrounding immense, nearly empty bubbles. This is the cosmic web, and it is the signature of gravity's patient work over nearly 14 billion years. It began with the almost perfect uniformity of the early universe. In the primordial soup after the Big Bang, there were tiny, random fluctuations in density, mere ripples, imperfections at the level of 1 part in 100,000. Gravity seized on these imperfections. Regions that were slightly denser had slightly stronger gravity, which pulled in a bit more matter from their surroundings, making them denser still, which increased their gravity further. It was a runaway amplification. Over cosmic time, the slightly dense regions became filaments and clusters. The slightly less dense regions were drained of matter and became voids. The small early variations were inflated by gravity into the vast architecture we see today. Dark matter was the crucial scaffolding for this structure. Because it does not interact with light or electromagnetic forces, it was able to start clumping under gravity much earlier than ordinary matter, which was buffeted by radiation pressure in the hot early universe. Dark matter collapsed first into a network of halos and filaments. Ordinary matter, the gas that would become stars and galaxies, later cooled and flowed into the gravitational wells carved by dark matter. The visible universe of galaxies traces the underlying invisible skeleton of dark matter. We see the luminous nodes and threads. Gravity reveals the massive dark framework that holds them all together. This structure is not static. It is a slow motion flow. Galaxies stream along filaments toward cluster nodes like water-down riverbeds. Clusters grow by accreting galaxies and whole smaller clusters. The cosmic web evolves, but it does so on timescales so long that to any human observer it appears frozen. Gravity works with a patience that dwarfs all biological conception. It took hundreds of millions of years for the first galaxies to form, billions for clusters to assemble. This architecture is gravity's masterpiece, painted with the broadest brushstrokes across the canvas of space-time. And within this architecture, gravity also acts as a diagnostic tool, revealing what we cannot see. The way galaxies move within clusters, for instance, betrays the presence of far more mass than we see in stars and gas. The phenomenon of gravitational lensing, where the gravity of a massive cluster bends the light from galaxies far behind it, distorting their images into arcs and rings, allows us to literally map the distribution of all mass, light and dark. The resulting maps show the dark matter halo in stark relief, a ghostly outline holding the luminous cluster in its grip. Famous examples, like the Bullet cluster, show two galaxy clusters that have collided. The visible hot gas, slowed by the collision, lags behind, while the mass inferred from gravitational lensing, the dark matter, has sailed through mostly unaffected. It is direct, visual evidence that most of the mass is something that interacts only through gravity. At this scale, gravity is no longer just a force acting on objects. It is the organizing principle for the distribution of matter in the universe. It is the sculptor of the cosmic web, the guide for galactic motion, the revealer of hidden mass. It integrates seamlessly with another, even more dominant feature of the cosmos, the expansion of space itself. And this brings us to the final, overarching context for gravity's work, an evolving, stretching universe where gravity's local pull contends with a global stretching. The universe is not static, it is expanding. This is not like an explosion in space, with galaxies flying apart through a void. It is space itself that is stretching, increasing the distances between galaxies that are not already gravitationally bound. This discovery reshapes our final understanding of gravity's role. We now have two seemingly opposing actors on the cosmic stage: gravity, which pulls things together, and expansion, which pushes them apart. Their interplay defines the fate of structures and the large-scale evolution of everything. The expansion was first inferred from the observation that distant galaxies are all moving away from us, with their speed proportional to their distance. Hubble's law. The farther away a galaxy is, the faster it recedes. This points to a uniform stretching of the fabric of space-time. Gravity works within this expanding backdrop. Crucially, expansion does not affect bound systems. The solar system does not expand. The Milky Way does not grow larger. Earth does not drift away from the Sun. Why? Because within these systems, gravity is strong enough, the binding energy is deep enough, to overcome the tiny background stretching of space on those scales. The expansion only becomes significant in the vast gulfs between galaxy clusters, where gravitational bonds are weak or non-existent. For most of cosmic history, gravity was the dominant influence on structure. It slowed the initial expansion, it pulled matter into clumps, it built the web. But observations in the late 1990s revealed something shocking. The expansion is not slowing down, it is accelerating. Something is counteracting gravity's pull on the largest scales. This something is called dark energy. Dark energy is not a force that pulls or pushes matter directly. It is a property of space itself, a constant energy density that, as space expands and more space comes into existence, causes the expansion rate to increase. Think of it as a kind of anti-gravity pressure embedded in the vacuum. The Planck satellite, along with other cosmic microwave background experiments and surveys of distant supernovae, have measured the cosmic budget. The universe, it seems, is composed of roughly 68% dark energy, 27% dark matter, and only 5% ordinary matter, the stars, planets, and us. This balance dictates the cosmic story. In the early, dense universe, dark matter and ordinary matter dominated, and gravity ruled, forming structure. As the universe expanded and thinned out, dark energy's constant density eventually came to dominate over the diluting density of matter. Now, and into the future, accelerated expansion is in the driver's seat. This means gravity's grand work of architecture is largely complete for this universe. the cosmic web is formed. New giant structures will not have time to form, because the increasing expansion will isolate regions before gravity can pull them together. Existing bound structures, galaxies, clusters, will remain held together by their own gravity, but they will become islands in a rapidly widening sea. Over trillions of years, they will watch as all other galaxies redshift beyond their visible horizon, leaving them alone in an immense, dark emptiness. Yet, even in that far future, within those isolated islands, gravity will still reign. Stars will still orbit. Planets will still turn. Gravity's local dominance remains absolute. It is only the global context that has changed. This perspective places gravity in its final, humbling context. It is not the ultimate dictator of the universe's fate. It is a local sculptor working within a globally evolving space-time. Its influence is paramount wherever matter gathers, but it yields to the meta-influence of dark energy on the largest scales. Gravity and expansion are not fighting, they are different aspects of the same space-time geometry, one describing local curvature, the other describing global evolution. And yet, even as we understand gravity's majestic role across galaxies and its contest with expansion, we are drawn to the places where gravity becomes so intense that it overwhelms not just matter, but our very understanding of physics. These are the environments that strain the fabric of space-time to its limits: neutron stars and black holes. Here, gravity is no longer a gentle guide or a patient architect. It is a tyrannical, transformative force. A neutron star is the remnant core of a massive star after a supernova. The force of the collapse is so unimaginably violent that it crushes atoms themselves. Electrons are forced into protons, creating neutrons. The entire mass of a star, 1.5 times that of our Sun, is compressed into a sphere only about 20 kilometres across. The density is mind-boggling. A sugar cube-sized amount of neutron star material would weigh as much as a mountain on Earth. The surface gravity is about 100 billion times stronger than Earth's. An object dropped from a height of 1 metre would hit the surface at a significant fraction of the speed of light. Mountains on a neutron star can be no more than a few centimetres high. Any taller and they would collapse under their own weight. The space-time curvature is so extreme that light is noticeably bent around it. Time dilation is dramatic. A clock on the surface would tick vastly slower than a clock far away. These objects are not just theoretical. We observe them as pulsars, rapidly spinning neutron stars that beam radiation like cosmic lighthouses. Their precise ticks allow us to test general relativity and strong gravitational fields, and they have passed every test. But gravity can go further. If the collapsing core is above a certain mass, about 3 times the Sun's mass, no known force in the universe can stop the collapse. Gravity wins completely. The matter is crushed to a point of infinite density, a singularity, and space-time is warped so severely that a boundary forms around it, the event horizon of a black hole. The event horizon is not a solid surface. It is a point of no return in space-time. The escape velocity at the event horizon equals the speed of light. Since nothing can travel faster than light, nothing, not even light, can escape from within. It is a one-way membrane in the geometry of the universe. Crossing the event horizon of a large black hole might be uneventful locally, no wall of force, but the future inside becomes inexorably directed toward the central singularity. The pull of gravity becomes so extreme that tidal forces, the difference in gravity between your head and feet, would stretch you into a long, thin strand of atoms in a process grimly called spaghettification. Near the singularity, the laws of physics, as we know them, break down. General relativity predicts a point of infinite curvature, but such infinities usually signal where a theory fails, where a deeper theory, one that incorporates quantum mechanics, must take over. This brings us to the final, and as yet unsolved, frontier of our understanding, the smallest scales. Gravity, described so perfectly by general relativity at large scales, refuses to be neatly integrated with quantum mechanics, the framework that describes the other three fundamental forces and the behaviour of particles at the tiniest levels. At the scale of atoms and subatomic particles, gravity is unimaginably weak, 10⁴40 times weaker than the electromagnetic force. It is irrelevant to their interactions, but in extreme environments like the Big Bang or the centre of a black hole, where densities and energies are unimaginably high, both quantum effects and strong gravity should be paramount. Our two most successful theories become incompatible. General relativity treats spacetime as a smooth, continuous fabric. Quantum mechanics requires everything, including fields and energy, to be quantized, to come in discrete packets. This unresolved tension is the quest for a theory of quantum gravity. Leading candidates like string theory or loop quantum gravity propose radical ideas that fundamental particles are vibrations of tiny strings in higher dimensional spaces, or that spacetime itself has a discrete granular structure at the Planck scale 10⁵35 metre. These theories are mathematically elegant and internally consistent, but they currently lie beyond direct experimental proof. The energies required to probe the quantum realm of gravity are far beyond anything our particle accelerators can produce. So, at the very smallest scales, gravity becomes an open question, a mystery. It is a reminder that our understanding, however profound and far-reaching, has edges. We know how gravity behaves from the size of a millimetre to the size of the observable universe with stunning accuracy. But at the extremes of the very small and the very dense, the map has blank spaces. Gravity does not fail, our description of it reaches its limit. This uncertainty is not a weakness of science. It is its engine. It marks the boundary of the known, the shoreline of a vast ocean we have only just begun to explore. From the barely there tug on an asteroid to the world-bending curvature around a black hole, from the patient weaving of the cosmic web to the mysterious quantum frontier, gravity reveals itself as a single consistent phenomenon expressed across an almost incomprehensible range of intensity. It is universal in its application, breathtaking in its variety, and humbling in the questions it still holds. And it is this same force, in its quietest, most familiar expression, that we feel when we stand up from our chair, when we catch a falling leaf, when we simply exist on this particular world. Which brings us, at last, back home. After a journey that has stretched from the infinitesimal to the cosmic, from the fragile hold on a speck of dust to the inescapable grip of a black hole, we return to the feeling that began it all, the solid contact of your feet with the floor, the weight of your body in a chair, the predictable arc of a thrown ball. It all feels the same. Ordinary. Consistent. And in the most profound sense, it is. But it is no longer only that. That familiar pull is now framed by an immensity of context. Gravity feels consistent because the human body and every living thing on Earth was sculpted within an extraordinarily narrow gravitational range. From the first cell division, gravity has been a constant, unvarying condition. Muscles developed to work against it. Bones grew dense to withstand its load. The delicate tubes of the inner ear that govern our balance calibrated themselves to its unwavering direction. By the time conscious thought emerges, gravity is so deeply embedded in the operating system of perception that it doesn't register as a separate input. It is the baseline, the 0 point. Our senses are designed to detect change, not constancy. A sudden lurch triggers alarm. The steady, eternal pull toward the centre of the Earth does not. It is the silent, trusted stage upon which the drama of life plays out. Earth itself provides this remarkable stability. Its mass is effectively constant on human timescales. Its shape and rotation introduce variations so minuscule that they are smoothed away by the scale of our lives and the coarse resolution of our senses. The brain builds a predictive model of the world where objects fall, where effort is required to lift, where balance has a certain feel. When these predictions are met effortlessly, moment after moment, year after year, the force responsible disappears from conscious awareness. It becomes invisible through sheer reliability. This is why the tiny real variations in Earth's gravity, weaker at the equator, weaker on a mountain, go completely unnoticed. They are buried in the noise of other sensory information. The body adapts to them automatically, without a flicker of conscious thought. Only when gravity changes dramatically, as astronauts experience upon entering Earth orbit or stepping onto the Moon, does it crash into awareness. The resulting disorientation, space sickness, the clumsiness of returning astronauts highlights how specific and deep our adaptation truly is. What felt like an absolute universal was, in fact, a particular environmental condition to which we are exquisitely tuned. So, we arrive at a quiet synthesis. Gravity is a universal feature of the universe. The same interaction, governed by the same geometric principles rooted in mass and space-time, operates from the scale of planets to the scale of the cosmic web. It is continuous. A neutron star's gravity does not contradict Earth's, it extends the same rules to an extreme limit. The simplicity we feel is not an illusion, it is the local experience of a universal law under very specific, very stable local conditions. The universe is not uniform. Mass is clumped in stars, scattered in dust clouds, woven into dark matter filaments. Distances are unimaginably vast, therefore gravity cannot be uniform. Its expression, the strength of the pull, the curvature of the path, the pace of time, varies from place to place, seamlessly and predictably. Our steady gravity is not the standard. It is one data point in a vast spectrum. It feels central. Because we are at its centre. This realization does not destabilize our world. The floor remains solid. The falling cup still breaks. Instead, it enriches the experience. That mundane sensation of weight becomes a connection to something cosmic. You are not just standing on a floor, you are following a geodesic through the space-time curved by an entire planet. Your sense of balance is not just a biological trick, it is a negotiation with the local geometry of the universe. The reliability of gravity is evidence of a deep underlying consistency in the laws of nature, not evidence of a simple force. Living inside one version of gravity means accepting that familiarity is not universality. It means understanding that our normal is a local custom beautifully adapted to, but just one possibility in a cosmos of stunning variety. We can now hold two truths comfortably, that gravity here is constant and dependable, and that gravity elsewhere is profoundly different. There is no contradiction. The law is universal, the outcome is local. Our journey shows that gravity is more than a chapter in physics. It is the great organizer, the silent shaper, the patient architect. It gathers clouds into stars, stars into galaxies, galaxies into the great web of light and darkness. It guides the planets in their endless dance and the spacecraft on their voyages. It bends light, stretches time, and reveals the hidden bulk of the cosmos, and at the same time, It is the reason a book stays on a table and a child can jump and come down again. We end where we began, grounded. The pull is still there, gentle and firm. But now, you can feel it for what it is. Not just a force, but a conversation between mass and space, a curvature in the fabric of reality, a local expression of a universal principle. You are living inside a specific, gentle curvature of space-time, on a world of a certain mass and size. That particular curvature is your home in the cosmos. It is what makes Earth, and the fact that you can feel it, rely on it, and yet now understand its place in a grander scheme, changes nothing and everything. Gravity works everywhere. It simply does not feel the same everywhere. And living inside this version of it is enough to remain grounded, connected, and at ease within a universe shaped by the same influence from the smallest grain to the largest web of galaxies.